our YouTube. I'm Iman Abisab. I'm the chair of the UAE ISTRUCT regional group, and I'd like to welcome you all to our CPD number 7 tonight, which is entitled One Za'abeel version 2.0. 2.0 because this CPD is basically a continuation of an earlier CPD that was delivered in 2019 by the same speaker and focused on the design of this landmark project. And this time, our speaker, Jens Fussing, is going to continue the story with a focus this time around on the construction of this project. Jens is a senior technical director at Rambol. Jens came to our Middle East region in 2001, and since then he has seen the region developing rapidly until now. Jens has over 30 years of design and construction experience in building structures with significant experience in precast concrete and steel. He specializes in high-rise buildings. Jens has carried out project and design management on numerous building projects across multiple uses. He's worked in various parts of Europe, Middle East, as well as Africa, Asia, and the Americas. Jens focuses on optimizing work processes, buildability of site production, simplifying the on-site processes, and applying high-end engineering solutions, high-performance materials, and as well as design optimization to ensure speed and efficiency. Today, as I mentioned earlier, Jens will take us through the One Za'abeel project construction with a focus on construction load cases, sequencing, and analysis during construction, as well as predicted versus observed movement during construction of this very challenging high-rise project. Just before I hand over to Jens, I'd like to thank our gold sponsor, Hempel. Hempel is a supplier of intermittent durability and fireproof paint for steel structures. Here you go. I'm ready to hand over to you, Jens. Thank you for kicking off, and please start sharing your screen.
Yeah.
We can see your screen. Perfect.
Okay.
Thank you.
Okay, I'll start now. Yeah, so this is one of the longest sky bridges in the world, and so the reason why we made this second version is because back in 2017, 18, 19, this was all thoughts in our brains. It was all computer models. So a lot of the slides from that time has now been shifted out with real photos, with real situations, so we can see our thoughts, how it looked in real life. So a lot of the old renderings is now actual photos from the real world. Yeah, so today we'll go through it a little bit similar like last time, but it's going to be a lot more precise. So we'll talk about the sky bridge, we'll talk about how it was constructed, how it was launched, the lifting arrangement, the movement, the theoretical side of the whole thing. And then of course, in the end, what was it we thought in 2018, 19, and what did we actually observe? And then a little bit about the theory, how to do these sorts of designs. So actually back in 2017, the contractor for this project here actually called me one day and said, can you come and have a cup of coffee? We want to hear how you would like to construct this building. And of course, I didn't know how to do that. So this was where the whole thing started. And then in 18, 19, it really kicked off with a lot of stakeholders getting involved into the project. But when we come to tall buildings, there's a lot of common denominators with regards to bridges which is connected. I'll just explain a little bit about that. So sky bridges in general it's a sky bridge which connects two buildings, for example, but the way they are constructed can vary a lot. So if we take the One Za'abeel first, that was a bridge which was launched and then lifted up into place. If we take the Jumeirah Gate, it was the sky bridge on top, was lifted up and then propped and then finished, whereas the opus was sort of a stage construction where you build from two sides and then you hope you can meet in the middle. Whereas the Dorchester, everything is vertical. There's actually nothing which is being launched. And then you have a project which was never built in Copenhagen, which was like a cable stay bridge, was also built in stages out. So there's many different ways of constructing sky bridges and also the use of the sky bridges. But one common denominator is always to have one, in this case, one ETABS model. So you get the behavior of the different building into one single model. That's one thing which always has to be there. So if we go into our project here, so we'll talk a little bit about a temporary platform. We'll talk about the highway, the lifting arrangement, how the bridge actually was connected to the tower movement during the construction and during the lifting, and then the critical path. What can you do before what? Because it's a two-way street, right? So your design forces depend on your construction and vice versa. That's sort of the interesting things about these projects here. So back in 2017, the next question the contractor said to us was, we have to meet the time schedule, we have to be able to continuously construct the towers while we're lifting. So of course the question was, how many floors can we continue constructing above the bridge while we're lifting up the bridge at the same time? That was sort of the scope of the project from our side, to define how does the building move and how high can we continue the construction while we're actually lifting the bridge and connecting the bridge to the tower. And so back in 2018, this was a hole in the ground, and we had the first CTBUH conference after it was started in Dubai before that. And then it was funny when they came here, the CTBUH people, to pre-arrange the conference. They said the first impression was, this type of structure hasn't been done ever before in history. I don't know if it's right, but that was what they said. So if you look at it, this bridge is situated 100 meters up in the air. And just to give you a little bit impression about how many people were involved. I mean, I had my team, let's say 3-4 engineers, but beside that, there was the local design institute, and there was the foreign design institute, and then there was RTA, DM, and Salama. So there was more people checking our work than actually working on the job. If you go back 40 years ago, it would probably be the other way around. So it's a little bit symptomatic about where our industry is going, that we actually today have more people checking than actually working. And of course, each of these people have to have opinion about different things. And I'll come to and show some of the opinions and struggles and how to overcome the things. So just a little bit about the dimensions. So the tall tower is called Tower A, that's 310 meters. And the B is smaller, 270 meters. The bridge itself is an 18 by 18 meter section. It's like, you can say, 4 floors. The total length is 226 meters. I think that's why they said never been done in history. The total length of the cantilever is 66 meters, and the last little tip there is 33 meters. So what? So there's many. So of course, back to the first question: how are you going to build this project here? You could imagine that you built a temporary platform across the highway. I mean, that would be the sort of, first intuition, the idiot-proof solution, like have a combined crash deck over the highway, and then you lift up the bridge itself. That's sort of the first intuition. But having discussions with different steel suppliers and the steel supplier who was eventually there, they came up with the idea to build the tower on one side and then launch it across to the other side and then lift up the tower. So all this was done at the same time, and the podium structure at the bottom was not designed for, what can we say, for all the temporary loads or the self weight of the bridge itself. So that meant that you can see all the things here with in yellow. That sort of, you can see this is where the bridge would sit in between. So I think this is from 2019. We had to extend the podium. Everything you see with yellow in the next slides is actually sacrificial. So when the bridge is lifted up into place, you can remove all the yellow stuff afterwards. So you have to imagine that now both the towers are being constructed. The temporary platform on top of the podium is being constructed. The gantry cranes, which is going to be lifting later on, everything is being constructed at the same time. Both temporary things and permanent things are being constructed at the same time. So this is just a snapshot of the extension of the podium. So the extension of the podium. You can say that the bridge itself was divided up into modules, which were then constructed on this temporary platform here and then slid across. So this was sort of like the factory on site where they would construct all the modules. And the sliding itself, it was like 8 segments. And it has a nose in the front. We'll come back to the why did we have that one. So all the sliding forces are actually internal forces, which is happening inside these. You can call them rails, like a train rails. We did design the podium structure for impact load of 5% in both directions. This was one of the compromises we had with RTA to do some extra safety on. This was one of the reasons, one of the convincing arguments for how and why we could launch the bridge across. The benefit about launching the bridge across the rail or the highway is, of course, it's very, very short time. You actually close your traffic, and it was, of course, always done in the nighttime. So that was how we convinced RTA to go ahead with the launching technique. And also, if you see all the temporary structure there on top sits on column underneath, and some of the columns didn't work, so we had to put more columns for the self-weight of the bridge itself. So here you can see that the bridge itself, or the highway itself, sits 20 meters above the what should we say, the ground floor. And then the platform itself goes almost hard up against the highway on both sides. And so it's a full operational highway, except when the bridge is being launched and lifted, then the highway is closed. Yeah, here you can also see, the amount of scaffolding to carry the construction, and also because sometimes if the column doesn't work, we need to get the load through alternative load pass down. I forgot to say that actually underneath the ground level here, there is 7 basements of parking, and if you could sort of turn the whole thing around, of course you could say, why are you building the bridge first and then you build this building afterwards? I mean, the highway bridge, shouldn't it be the other way around? But these are the circumstances, so that's why first the hole in the ground, and then you build up, and then you need to get across the highway with the bridge itself. I mean, with the sky bridge. So here you can see this, all what you see here, all the yellow. So you can see, for example, if there is a concrete column, there's like a yellow color on both sides of the concrete columns. This was because the concrete column was not designed for the load of the temporary situation where the sky bridge was resting on the podium structure. So separate ETABS model had to be done of all the ground structure to see where did we need to strengthen the permanent structure. As soon as the bridge is lifted up, all this yellow stuff goes away again. It's not needed anymore. So that in itself is a tremendous amount of calculation work, and also again with the 5% horizontal load from the sliding, justifying all that stuff. So this was sort of the what should we say, the idea behind it, how to strengthen the podium structure itself, so it could carry the weight of the bridge itself. So here we see these what's it called? It's like a railway, right? So we have the feet. So in each node of these 8 segments, we have these feet, which is then also temporary. So the feet is welded onto the bridge section itself. And you can see there are these small plates here. This is like, it's not Teflon, but it's similar. So it has a very, very low friction coefficient. So you can slide across. So the bridge can slide on top of these this railway here. I just go to the next one here. So the way the bridge is what should we say, launched, is that we have strand jacks horizontally. So first, while the bridge is constructed in modules, each module is then slid across, so you can build the next module, the next, through horizontal strand jacking. And then, of course, afterwards, when the bridge goes up, it's vertical strand jacking. So all these yellow feet here are sacrificial, and they're only there for the purpose to sliding the bridge from one side of the highway to the other in one piece. That's the only purpose of these feet here. And before the bridge is lifted up, then all these feet here are cut off and actually thrown out, and that doesn't have any more purpose than that. And here we can see that the dead and the live end of the, what can we see, of the pulling mechanism when we slide across each what should we say, each module. And each module is then, when the first one is constructed, then the next one is put up against it and they're welded together. And of course, these welds are designed for a combination of when the bridge is sitting up in the air and it's part of the moment frame and the slitting forces, and when it's cantilevering over the highway in its own, the worst envelope of all these situations. That's what the bridge is designed for. So here we can see the first, here you can see how, so the purpose of, we call it the nose, the yellow nose. The purpose of that yellow nose is to sort of catch the other side of the highway. So those 2 feet there in the front will catch railway sitting on the other side of the podium. And here you can see the first 2 modules are being connected and welded together, and then it's being slid across. So this was the first time that the, what should we say, the nose was sort of cantilevering over the highway or right before it. And the skidding speed, I mean, in the beginning, of course, there was a lot of what should we say, testing about how to do the skidding. There was a lot of training, but as the team got more, what should we say, comfortable with the situation, they could actually slide up on around 3 meters per hour. So the first one was tricky, then it became more and more easy, and then in the end, it was just a one night exercise, and then you could slide the next module across. So now it becomes funny, right? So this was just before you can see the rail rates there on the other side. So this is just before we catch the side over here. So this is the situation. So underneath this podium structure here, there are these yellow columns here. And this is again the situation that the concrete structure was never designed for all this overhang here. So this is sort of the worst situation when you have a cantilever steel section hanging out, giving a force down into these yellow columns here. So as soon as the bridge was lifted up, then all these yellow columns here could actually be taken down. I don't know if you drove under the, what should we say, under the bridge in these days, but it was quite amazing to see how when it went with the overhang. Just a funny little story. here you can see the bridge is just catching the bridge on the other side. And I will say I have full respect for these strand jacking specialists, because when we were launching the bridge across horizontally, the bridge was actually 170 millimeter off. You could see it. It's not gonna hit when they were launching across, but by pulling a little bit more in one side of the rails, it actually came back into place. So we could see it was going to land. Then the next thing, they were now lined up in front of each other, but the foot was actually lower than the railroad, so they had to jack it up again, and then they could go in and catch the railway on the other side. It's just by playing with the forces in the strand jack, they could actually guide the bridge into place. And now you can see here, this is the touchdown, and of course there was a big celebration that evening when we had that touchdown. So now all of a sudden the static system changes. Right before it was a cantilevered nose, but now it's actually more like a simply supported with a backspan on the other side. So all the forces will now change in the bridge, and it will change on the reactions. So all those envelope of forces during the construction, of course, needs to be studied, and all those envelope together with a permanent situation. That's actually how the bridge is designed, so it can take all the different load situations during construction and also in the final situation. I'll just come to some of the. So now in the bottom, so while the bridge was being what should we say, launched in the bottom, at the bridge level itself, there's also some preparation going on. So that's what I'm saying. There's many activities happening at the same time. So what was happening above the bridge, there are some lifting gantries being erected, and also this is also where the mechanical rooms are and where the outriggers are. So inside the outriggers, a lot of embedded steel is cast into the walls. A lot of these steel sections, which you can see here, are in a way also sacrificial, because they're only there because in the lifting situation of the bridge. So if you could take them out, you could actually take them out afterwards. And it was also done on the safe side in such a way that when we designed all the steel we needed all the blue steel here, we ignored all the loads on top, because of course the more load you have on top, you could probably take some of this steel out. So there's some conservatism built in to the system itself. And of course, I mean, so one of the things which happens when you lift is that because of this assumption, you will have some locked in stresses. Again, it's about finding those envelopes, because you run the ETAS model in the end, then you have this situation, and then you can actually end up in having some locked in stresses, which you need to deal with. The member sizes all remain the same as per the original, what should we say, design. So this is from the, what should we say, this is from the steel suppliers Tekla model of the steel itself. So what you can see here is that there is all the gantry cranes, how it's lifted up. Actually, this is wrong, because these feet here were actually cut off before the bridge was lifted up. But there's a little bit of data to look at here, and that is that. So a big discussion is that if when you have temporary structures, should you then design for earthquake? There are a few clauses in some of the temporary, what should we say, ACI codes. If you fall into certain categories, you can actually ignore the earthquake, and some other times you cannot. But in this case, we could actually ignore it. But there was a lot of, what can we say, pressure, especially from RTA about the safety. So anyway, so it was a lot of compromise back and forth. So what we agreed on, and you can say with some literature, of course, also, was that when we lifted itself, that we would take into account an impact load of 15%, and also horizontally, both direction, an impact load of 5%. So so there's no earthquake, there's no wind in this situation here. Only the time when we lifted, we have assumed for extra impact loads, simulating some earthquake or some safety. And there will also be impact, of course, because when you lift, but I don't believe it never can come to 15%. So it's a little bit of conservatism. So one of the funny things is, if you think about the lifting of the first segment itself was 8,570 tons. I'll come back to this in a minute. Without the nose, just remember that number. So, and this is just another, what should we say, a little bit about the structural system. So here we have shown the embedded steel inside the outrigger wall. So you can see that, for example, on Tower B, there's 2 lines of vertical and horizontal, you can say, load-bearing lines, and in Tower A we have 4 lines of load-bearing. And that's of course because of the cantilever. So Tower A takes the most amount of load, and of course the corner column at the tower will take a lot of load. We'll come back to that in a little bit of time also. Just the thing, if you see here, there's some steel connecting between the tower and the bridge itself. I'll come back to that and tell how that is done, because that's one of those, how do you do that connection between the tower and the steel itself? But in each column where there is a load path, there is an embedded steel column inside the concrete column. And just a little funny thing about the pre-campering. So the whole end of the whole 66 meters here are actually pre-cambered, and the last 33 meters is also pre-cambered. But the pre-camber is in 3 dimension, right? So if you imagine that you actually make it so it's also twisting, so that when it comes down, it's horizontal in a 3-dimensional pre-cambering. So of course we discussed a lot about when to lift the bridge. I mean, should it be the summer, winter, or what? Anyway, we ended up, the real lifting was in the fall, and it was of course to minimize the expansion and contraction of the bridge itself. So the connection between the bridge and the tower itself is done by, there are diagonals, there are some stop beams, and then there are some diagonals, and the diagonals are in the planes of the bridge and also horizontally in the load lines. And because when you lift the bridge, the towers will, of course, they will move, but they will also twist, because the loads are not the same in each column. So it's insanely difficult to predict the member sizes, I mean the member lengths. So what we did was we said, fine, we can't predict that, so we will lift the bridge up, and then each and every diagonal and stop column was actually site measured, and there was 72 independent pieces of steel welded to the steel bridge and the composite column inside the tower itself. So that was sort of the philosophy. As soon as the bridge was lifted up, then you start site measuring and producing all these members, and then you weld everywhere at the same time. That was what happened at the site. This is just a little bit more, what can we say, accurate drawing of the embedded steel inside the outrigger walls. So what I'm trying to say is that, so indicatively, these pieces here are shown like that, but in reality, it was actually completely site measured and customized in the factory, and then brought to site and welded between the bridge and the composite columns on site. So here are just some fun facts, and you can see here, if you go to the top here, that the first section of the bridge was 8,570 tons of steel, and this is one of those things. The Eiffel Tower itself is 7,300 tons, so the lift itself is more than the Eiffel Tower in 24 hours when it was lifted up. The total weight of the first lift plus the last lift of the little nose is 10,100 tons of steel, which was lifted up. Here are some photos from the, what can we say, from the real world. So the gantry cranes are like small factories. So inside the mechanical floor above here, there are the lifting specialists are sitting with all the monitoring equipment, and they're adjusting all the, what should we say, all the strand jacks. Here you can see right before the lifting, the bridge ready to being lifted up, and with these extra gantry cranes erected on the end for the last 33 meter of tip, which is going to be lifted up a few days later. And so the first thing which happens is that when you lift the bridge, we can just see that's a few more of the how much equipment and stuff there is up at these levels here. So the lifting guys will sit in like a little control room where they can monitor everything when it's lifted up. I'll come back to how the lifting itself happened. So first, you can see now here the feet are now cut off. So the first lift. So first you make sure that you have tension in all the strand jacks themselves, and then you cut off the feet. And then the first lift was like a test of 100 millimeter, just to get a feel for the whole thing and make sure that we had the same forces in all the strand jacks everywhere around. And then the next day, even more, go up to 100 millimeter of lift to get more comfortable with the whole thing. And then from the 100 millimeter and up to the top, it only took 12 hours to do that, the lift itself. But a lot of the time is actually calibrating and adjusting so it's both forces, but it's also geometry, making sure that it's in the right place at the right levels, and everything is being monitored. Now you can see the bridges in its position before, after the lift itself. And now if you look down here, you can see all the temporary platform at the bottom there. You can start taking it away, removing it, and finish the podium construction after this one here. So before the 72 pieces of diagonals were site measured, we had to lift up the last piece of the tip. You can see it's down there in the bottom, and it's almost the same principle. The first day, 100 millimeter, 1 meter, and then you go all the way up. So from the first lift of the long section to the last lift of the piece here was about 8 days. Then all the lifting was finished. And then now you can see here how it looks when it's lifted up. It's actually some nice photos considering this is October, November. And that now it's in place. So from this point of time here, the connection of this last tip, all the 72 site measured pieces could be done, right? So now all the focus is on getting this tip welded onto the big part of the bridge and getting the connection done between the towers and the bridge. So an insane amount of welders were on site at this time here. Let's just see. So here you can see how it looks down through the whole bridge when it was in place. Now this is where all the site measuring starts and all the welding starts of the connection between the bridge. So the welding of the tip and the welding of the 72 pieces, which was connecting between the bridge and the tower, took 45 days, 1.5 months to carry out the welding itself. And from that point of time, you could then start to remove. You can see the strand jacks, all the jacking and the gantry. All that is now then sacrificial. You can take it all down. You will never use it again here. So then you could continue with all the interior stuff inside the bridge. So now a little bit about the theory of the building movement study. I think I showed this one here also the last time. I'll go a little bit quick through this here, but I mean, so this is the situation that we have a tower with sort of a bridge hanging. It's with a very eccentric load, and then what happens? So when we do the building movement study, there's many different things which impact. I mean, there's elastic, and then we come with the stiffness, concrete development. It settles. That's why it's a nonlinear design. We put the bridge up, we get eccentric loads, we apply other loads, we have creep shrinkage. So to see what happens with the bridge itself. So remember that the contractor asked how many floors can they construct before it becomes too wild. I mean, with the deflection of the tower. I'll come back to that now. So this is the usual thing we do when we do sequential construction, that we take all these what can we say, parameters into account, and then we see how does the deformed shape of the building look. So why do we study deformed shapes? Yeah, it's because of we want to know what's happening with the building. And of course, if we have an ideal situation with a core in the middle and the same spacing to all the columns and the same distance and the same load and the same stress, the building would settle almost evenly. But in this situation where we have very high loads on some columns and smaller loads on some other columns and a huge eccentric load on the side of the tower, of course it will the tower will deform when it's constructed due to the load and the sequence of construction. So the easy one, of course, the easy part of the equation is the elastic shortening, which is we have learned from school, right? And then it starts to become more complicated because now we have to look at shrinkage, which is the design dependent stuff. And I would just I'm not going to get into too much of this. I'll just say that's okay. So if you look at shrinkage alone, just to tell how many. So shrinkage is time dependent. It's humidity dependent. It's about it depends on its curing time, temperature, slump, aggregate type, air content, cement content. All these things has an impact on how the shrinkage is going to occur. So one little thing which I like about this graph here is if you see there's something called 10,000 days out here. If you notice the latest thing with the municipalities here is that they all require a 10,000 day building movement study for all the towers here. And I think this is probably where they have it from. So if you go 10,000 days or if you go 20,000 days, it's not a big difference, but it sort of plateaus off around about 27 years. The shrinkage, what can we say, the time dependent effects. This is just a lot of things I'm not going to go into because this is a whole talk in itself. A lot of things which will affect your shrinkage of the concrete. The same thing happens with the creep, almost the same parameters, materials, weather, expose, all these things, and creep is the biggest component of the time dependent effects. And again, if you look here, 30 years, 27 years, it plateaus off. Again, I think this is where the municipality have this 10,000 day rule from. I know today that when we make a tower, we have to do a 10,000 day building movement study. It will not be totally correct because we don't know the real construction sequence, but it will almost be there, right? So I think it's a good rule. I mean, it's a good estimate that we have that now in the I don't know if it's in the building regulation, but it's at least always you have to do it to get through the authorities, and I think it's a good idea. Again, I will not come into all these. I'm just trying to emphasize how many items and how many parameters which actually affect your building movement study. So in short, I mean, we have so the thing is that this project here is going to meet 2 winters and 2 summers. So you will never get it right. Temperature, humidity, radiation, a lot of things will impact the, what shall we say, the final result. So you can choose to do different scenarios, or upper bound, lower bound, different scenarios of construction and materials. But one thing I will say is that you can at least try to get your estimates as correct as possible. And of course, one thing is that I know we've been having the discussion about should we use measured e-values or real e-values. Well, in this case here, you should use measured e-values, right? Because that is as a good assumption as possible. So I'll just go into the. I'm not going to go down into each and every load sequence, but together with the contractor, we have to agree on a, what can we say, on a construction sequence. What's going to happen when, and then you can replicate that in your ETAS model. So in this situation here, there was like 35 different construction stages, and our scope actually ended when we reached the top of the tower. This was sort of what you can say the original consultant wanted to know: what happens with when we construct the bridge itself, what happens to the tower. So again, one model, as good estimate on the load as possible, a good estimate on the materials as possible. And again, this now it's a nonlinear SLS model to actually find out how does the building behave. So now comes all the fun. So to answer the contractor's question, we found out that the flipping point for Tower A was 14 stories. So actually, while all this bridge stuff, all this what you just showed, the podium and the bridges, all that was done, sort of the point where we would start to see huge deflections on Tower A would be if you constructed more than 14 floors above the bridge. And for Tower B, it was 10 floors. But that's also like, 10 floors, that can easily be like 3 months on a time schedule. So of course they wanted to do that. So here you can also see, so this is how the bridge and the towers actually rotate because it's so eccentric. If you look at the ETAS model and the SAFE model with these deflections here, 137 and 150, there was actually nothing wrong. It passed ULS, it passed SLS. It actually passed everything. But the thing was that in the original specs, this was from Nick and Seki, in the original spec, there was a clause which said that the largest tolerance accepted would be height over 1000 or 50 millimeter, or a rotation of plus minus 25 millimeter. So even though the tower works, it works for just normal deflection and ULS, we had to go back and look at how do we make the tower more straight. So I'll just want you to look at this so you see you can have, so at the bridge itself, when we're there, it's about 60 millimeter of movement when you lift up the bridge. So what we decided to do was to preset the tower. So it was actually constructed out of plumb. So for example, if you take Tower A, the blue line, this is how it will look when we lift the bridge, and then you can continue constructing up to level 14 and make sure the bridge is there, and then you continue up. And then we did another exercise where we started to preset the tower itself so that we could conform with you can see the 50 millimeter here, right? The 50 millimeter what should we say, tolerance. So what we decided was at certain level, we would preset the tower out of plumb, I mean, the reverse of the direction which it would then move in. I know this sounds very easy, right? But this was a lot of discussions and a lot of analysis to find out where to do these things. So I'll just show. So this is sort of a little bit diagrammatic, how to show how to do these things. So the in different levels, we would then offset the tower 15 millimeter away from the bridge, so that when we lifted up the bridge, it would then come back in. And there was also a higher level of presetting just to even that movement of the whole tower out. So the practical, what can we say? The practical, how do you offset a jump form? So you actually had to be able to shift it 15 millimeter at certain level, but at the same time, the composite columns are 3 to 4 story high steel sections. So they had to be tilted in that direction and then filled out with welding. So it was like 2 different ways of doing the offset itself. So here you can see this is that corner column sitting with a huge load from the extreme load of in Tower A. If you see up here, there's a little box. It's like a tent, and there's like two welders and 2 preheaters. So that's 4 people sitting inside here. So one is preheating and the other one is welding all the way around the column. And the irony is, normally we hear that the core and the jump forming is the critical load, critical path on your time schedule. But in this situation, it was actually the composite columns, which was the critical path on the time schedule. Each splice, so you can see this is my foot. So each splice around for these columns here would take about 3 weeks to weld, 24 hours per day, and it would weigh around 1.6 tons of weld continuous. So that was actually the critical path on the time schedule, was the composite column connections. And then we did the usual, I'm not going to get so much into this. This is what we have to present today for the authorities. I mean, the differential settlement from core to the column. So all this was then reported back to the facade engineer at different floors, at different height on the different towers. So now I'm almost coming to the conclusion which we have been waiting about, and that is that so during the process of first finding out what happens to the tower, how do we preset it, and then you can say, okay, how do you actually make sure of that? So what we decided was to actually have 200 monitoring points. What you cannot see on this here was that we also monitored the raft itself and the core, because there will be a little bit of dishing inside of the core itself underneath the piles. But 200 points, you can say measuring points, and that's different, just normal points where you can measure, but also prisms and strain gauges, tilt meters, and other things. So, and of course, so it's the yellow ones which is of most interest to see how the tower itself would behave, and we were mostly looking at the core itself to see how that was moving as a consequence of the construction load and the bridge lifting. So you can see here we have the four points of Tower A and 4 points of Tower B. And so what is interesting is that so this is when we lifted the bridge. We monitored what is happening with the towers. So the dashed lines is the predicted behavior of the lifting. That's how we thought the tower would behave, the dashed ones for Tower A and Tower B. And what can we say, the full lines in red and blue is the measured values on site. And you can see that it's quite amazing. It's within plus minus 10 millimeter what we measured to what we actually predicted would happen to the tower. And this was sort of the, you can say, this is what gives you the job satisfaction, that you really get to see what actually happened with the whole thing. So there was a quite good what should we say, quite good correlance between the predicted values and the, what should we say, measured values. And the reason why we have some of these S shapes here is there was a few mistakes on the measurement, but I mean, the big picture is that it follows nice and clean. I'll just, the last little topic here, I have 5 more minutes. Just about the sensitivity of the, what shall we say, of the materials when you do building movement study. I mean, this is the Jumeirah Gate building. The Jumeirah Gate building is not symmetrical. It has a little bit eccentric because, of course, the cores are pulled back and you want the view over the sea. Some years ago, we were asked to do the same, but in this situation here, we were asked to do a long-term building movement study. What happens to the tower after, you can say, the 10,000 days, both as a vertical displacement and as a horizontal displacement. And here we have the different types of, for example, this blue one is only if it's elastic, then you take into account sequential construction. We always have the biggest compression in the middle. And then you can start taking into account all the time dependent, what should we say, parameters, just like what we talked before. And this is vertical movements of the floors. I just want to show a few graphs here, and that is just, again, one of those things which I talked about before, that you can see, for example, if you go into the ETABS and you can choose to either use your ACI or FIB, you can see the difference in creep and shrinkage. It's different development curves, right? And in the same time, we still have all the other things which we just talked about, right? Humidity, temperature, curing, composite, and strength development. So that's why there is no exact result to these analyses here. And this is a little bit the same, that so when you choose to either go to ACI or whatever, you have to decide all these correction factors. And again, also Jumeirah Gate, it also had 2 summers and 2 winters, right? So you will never get it totally right, but you'll get it almost right. And that's why you have to do the, what should we say, the monitoring. And the last little funny thing, I like this graph here, and that is, so for example, on this Jumeirah Gate, when we did the building movement study there for vertical, what can we say, settlement after 10,000 days, if you take the blue curve, this is if it's done as per ACI. And if you take the orange one, this is if it's done as per FIB. So you see such a big difference just by choosing 2 different codes. So yeah, maybe the real answer is the average. I don't know. I'm just saying that when we come to these sorts of analysis, you need to do different scenarios and envelope cases, because you can't get it right because of the difference in seasons over the year and difference in codes and assumptions. And that's actually why you need to do the, what should we say, many sensitivity studies and the building monitoring, so you can see, does it fit with what you have assumed originally. So yeah, here is a difference of, if you do it as per ACI, it would be 65 millimeter permanent settlement. If you do it as per FIB, it would be 100 millimeter at the top. So that's just how it is. Just to come back to the one Za'abeel, I think the time is perfect. Yeah. So this is back in 2020, the same day where you can see that the nose was lifted up into place. And then you have 1 year later, October 2021, where the cladding is almost done. And then again, I took this last January when it was handed over. My point with these 3 slides here is that the last 3 slides of the timing is that these type of projects take a long time. I mean, if you think about it, the first time we were sort of involved was in 2017. Then we started to get really into this 18, 19, and it was handed over last year, half a year ago. That's how long time these projects takes. Also because you need to go 7 stories down to excavate and build the basement. So I mean, these projects, it's not something which is done in a few years. It does really take a long time to construct. I'll just show you a few photos of a few slides of the. I want to skip this here. I want to just show you. Here's how. So this is in these rooms where the lifting specialists are sitting. So they have monitorings. They know how much force is in each jack. They can see where the bridge is. They have forces. They have geometrical equipment. So they know exactly what's going on with the bridge. So it's just like a little mixer pult, so where they can play with these things. And here they can actually measure the time and speed and height while they lift the bridge up into place. So that's how it looks from the control room when they lift the bridge up. I think that's it, precisely 8 o'clock.
Thank you, Jens. Thank you very, very much. Very, very interesting presentation. Very, very challenging project indeed. Now I understand why you've asked the question, which is bigger, the Tour Eiffel or this one? You were referring to the tonnage of steel, 8,500, I think, tons for the bridge. Yeah, that I wonder the sacrificial steel as well, how much more there was there. I hope they were able to reuse some of it as well.
Yeah, that's right.
Must be a lot. Okay, so thank you, Jens. I'm gonna open the floor now to questions. And we've got the first question coming from the YouTube channel. I'm gonna read the question, Jens, to you. Question from Prithvi Narayan. At what stage facade installation started? And how are these building movements measured versus calculated, taken into account, I presume? How did they impact the facade?
That was so if you saw the what's it called? Let me just see if I can go backwards. There was these plans, so each and every plan was actually part of our scope. Each and every floor plan we had to do what can we say, the differential shortening study. I'll just come back to that. You can actually see this slide here is quite good, right? So the facade was actually following up on this. This is what I'm saying, that the time pressure was totally crazy. So you had to follow the building. So you can see the facade is actually following up along the construction itself. And I will just show you so for each floor plan, we did these plans here so that we could what should we say, report back to this is for the facade engineer and the brackets. This is what it's about. So that you design your brackets for the correct, what can we say, interstory drift and the movements and all the different type of movements you have for the facade installation. And of course, I know in terms of facade engineering, the more movement they have to take, the more expensive the brackets are. So it's always about getting that number correct. So in a part of this, of course, there's also the movement between the middle of the span out to the column. All those are also reported in a long spreadsheet. So that was actually how the facade installation was coordinated with these plans and then following the construction program. Yeah.
Right. Thank you. Another question from Tariq. Very nice presentation on a challenging project. Thank you. Did your team also study performance-based design for wind?
I forgot to say that. Actually, during the wind tunnel test, there was actually wind tunnel tests for for the final situation. So that is of course performance based. So that's not code, because you cannot find this building in a code. So first of all, you have to do a wind tunnel test because of the geometry for the final situation. But there was actually also performed wind tunnel test at the, what should we say, during the temporary situations. So for example, when we had the bridge hanging there, we had situations where we designed for wind also just to see, but it was not the normal ultimate wind. It was a reduced wind because you can reduce your wind load for the temporary load case. So that was also done. And it was RWDI who was the wind engineer on this project here. And even the whole bridge, I mean, there is so for example, if you, for the cladding project, so each tower and the bridge, there's like a zone map where they unfold all the facades, and the same for the bridge. So each plane of the what should we say, of the bridge has an unfolded drawing where you can see all the pressure coefficients, so that when you design your cladding, you design it for the right pressure coefficient. And sometimes it's a little bit more than you think, and sometimes it's lower than what you think. It's actually quite interesting. Yeah.
Indeed, yes. Thank you. A question from Shapur Mekar. What was the difference between the measured E values and the codified ones?
I can't remember. I think it's about 10-15% higher. I mean, today the municipality, they do allow to use measured E values, but you have to. This was part of the whole rewriting of the Dubai Building Code, that they do accept it, but then on your drawings you have to make a drawing note that it has to be reconfirmed that the tested values. There's a special wording about how to do that, but I think it's about 10 to 15% higher. And I mean, this is the thing, right? So the thing is that the codes are, you can say, if you go to BS and American codes, are written for those regions, right? They're not written for this region, and you do get a lot higher E values here than those countries in where they're written. And that's why I remember way back when I was working in United Precast, we were doing Holocaust slabs, and there was a cap of, you could not design a Holocaust slab more than C60. This was just a rule. But they were all C80, and you could get C80 very, very quick. And that's because of the aggregate and the cement that we have here in the UAE. It's actually quite good. So that's why we get a lot better values if it's done correctly, right? So why not take advantage of that? Yeah.
Right. Thank you, Jens. Another question from Dr. Shapur. Was there a wind speed limit for launching or lifting the bridge?
Yes, I just can't remember what it did. So all of that was discussed. So the day we lifted, it was completely, there was no wind at all. I can't remember what it was, but there was a limit where we say if it's more than, so it was actually, we actually started 2 weeks before the lift to follow what is the weather going to be, the weather forecasts, to see if it was still reasonable, and it was discussed every single day. So I just can't remember what the wind speed was, but that was taken into account also. Yeah.
Sure. A question from Suhaib Akhtar. For this type of construction, when we are choosing the types of truss bridges, what knowledge goes into that? If you were to choose a different one for this project, which one would you choose? Would you choose another? It feels like a chartered membership exam question.
It's actually back to the very first slide I showed in the beginning, right? Because I have also asked, because I've done Opus, I've done maybe 5-6 buildings like this, and then of course then you start to think about, okay, well, what is actually, where is that sweet spot? When do you choose what? In my mind, it's about the aspect ratio. If you have something which is very stiff and a little bridge, that little bridge cannot give you any, what can we say, it cannot contribute to the lateral stiffness of the building. But at a certain point, it actually starts to help, like a portal frame, that's where, and I'll say, if you have that little bridge, which doesn't have any stiffness, you need to have them sitting either as fully propped or a roller joint in one side. Of course, it depends on how much is the deflection of the two buildings. So you can either choose to say fully propped or roller joint, or if it has a bigger aspect ratio, so it actually starts to contribute to the stiffness, you can use it as a structural member. So for example, the Opus, which I showed before, and the one Za'abeel, the bridge actually helps as a portal frame for the structure itself. So it's like a three-piece of structures, right? You have your towers, and then you have your bridge, which is like a moment stiff connection also. So in this situation here, of course, the box, because it has to be very rotational stiff. So of course you want to have all these diagonals to stiffen up the whole rotational. But if you have a bridge which sits nice and clean on clean supports which move the same, you might only need to have trusses in two sides and then just for wind at the top and bottom. So it's a little bit about what is the aspect ratio and what type of forces do they actually take. I don't know if that covers it, but it was a big, yeah.
Right. Yeah. Thank you, Jens. A question from Sama. A great work by all stakeholders. Any safety issues while the bridge lifting or construction is happening for this project? Did you have any alternate method for launching during concept?
Yes.
As I can see a lot of material. Yeah.
So the reason why we chose to launch it was actually to save on that. When I say save on that, that was a joke, because the alternative would be to construct a crash deck all the way the highway for safety. And then of course we came up, so this was Eversenda, and if you notice, they did the same type of bridge down, I forgot what it's, down by Mall, the Dubai Mall. They did the same technology where it was pre-accepted, because they sort of laid the stones for this one, because the launching itself is only 10 to 12 hours and it's done through the nighttime. So when you launch, you stop the traffic and there's nothing which can fall down, right? It's completely clean steel structure which goes out. So that was sort of the part of the optimization. The alternative would have been to build a full crash deck all the way across. But when the bridge was up in place, there was also a little safety net and crash deck which was actually hanging from the underside of the bridge to catch falling hammers and materials and whatever. But when the bridge was launched, the highway was closed. And of course, I mean, this was really debated. I mean, because you can discuss these things forever. I mean, what's the easiest and the fastest way? My first intuition when I saw the project was to build a platform from one end to the other of the bridge, full crash deck, and then lift the bridge up. But that was actually optimized further by the steel supply with the launching technique and saving time and materials. Yeah. Right.
A couple more questions, Jens, if you don't mind. Yes. A question from Omar Hayat. Did at any stage the loads on the foundation exceeded the final loads? So this is about foundations.
No, it didn't. And so the thing is that I've been thinking about that. The problem is that I'm starting to forget things because I mean it's correct, because we strengthened the podium structure, right? And so the columns couldn't carry the load. Then how could the piles then, right? But the thing is that the raft underneath the whole building was a 4 meter thick raft on piles per like 3 meters apart, right? So of course it does work, but I've also been thinking about how can it be that the column didn't work, and what about the piles? It can only be because the raft was so thick. I remember when we casted the raft, it's a 4 meter thick raft with T42s in both directions in layers. There was a steel structure inside the raft to carry the bars, which was going to be permanent in the sacrificial steel structure. I mean, not just some small bars, but a real steel structure carrying the bars itself. So yeah, good question.
Wow. Yeah, yeah. Okay, I'm going to take a question from the YouTube, a question from Ahmad Abdallah. Thank you very much for the great presentation. Do you think it was better to do the bridge lifting while the tower is not completed and to avoid the bigger part shortening that has occurred?
Yeah, so I mean the original thought, if you go back to one of the first slides, the original thought about the whole provocation of the whole thing was that there was a time schedule which the contractor had to finish, and then there was a design. The design said, build your 2 towers 100 meters up, then construct your bridge, make sure that it's fully connected, and then you can continue. That was half a year lost on the time schedule. So the contractor had to continue with constructing the tower. So I will say this is sort of a consequence of how it was tendered out, the way we chose to build it. So yeah, and I understand why the original designers they did it, because it was it was bulletproof, and it was one way to do it. But there was so much pressure on the time schedule, so we had to do everything at the same time. And you can actually see the facades following right up underneath the bridge itself.
Yeah.
So yeah.
A question from Mahmoud Ismail. Many questions from Mahmoud. Thank you very much, Mahmoud. Great questions. I'm gonna try to take 2 of them. The first one is on the yellow nose gens, which was used during the fabrication and assembly of the bridge. Was it to decrease the length of the bridge in the cantilever stage, to decrease the stresses, or was it used for another purpose?
It was actually a guide, right? It was to catch the other side of the. So when we launched the bridge across, it was sort of to have something to rest on and have that direction. That was the only purpose of the nose, like a guide, like a little guiding rail when you need to find the the location, the direction. So that was the purpose of the nose. And the funny thing was that while you were constructing, module number 8, the nose was cut off down in the other end at the last launch. So many activities were happening at the same time.
Yeah, right. And the second question was, you've mentioned, Jens, that the whole design acts as a portal frame with the 2 towers and the bridge. Did you design the towers also as a standalone, as 2 individual towers as a worst case scenario?
No, not for this one here. No, it was not necessary. Even if you look at the what should we say, at the half tower. But I agree to the question and the concept and the principle, because we do see sometimes we have towers, say for example your core wall is way ahead of the rest of the framing, that you need to check and see, can the core actually stand free 5-10 stories, but not in this case. We didn't do it.
Okay. And we'll take the last question from Ahmad. Great question, Ahmad. There were too many sources of deformation, Jens, that you've mentioned, the differential shortening, lateral movement, foundation settlement, and so on. Were they all considered together for the design of elements in one model, one analytical model, or did you handle them separately, then combine them?
No, they were all in one model, but it's quite interesting that you say that. I mean, so the original consultant was Nick and Seke, and they actually had 50 independent ETABS models. I mean, with combined model to find all those different sorts of scenarios, different ways of construction. So they had 50 different models of just scenarios. Do you build up? Do you build down? When do you build this? What is the weight of the bridge? So yeah, and all those envelopes. So I think there was. I mean, I showed the drawing around the outrigger level and the mechanical floor and all this embedded steel. If you go and take the original column and look what's inside that column, yes, we had to put extra reinforcement in here and there to make sure that the forces could go through the framing in the temporary situation. But all the member sizes, I mean, the geometry of the core walls and the columns and the blade walls remained the same. but everything was rechecked as per this, what should we say, lifting methodology. All the member sizes has been rechecked for the final way of construction.
Right.
Yeah.
Great, Jens. Thank you very, very much for an excellent presentation tonight. Thank you for your time. I don't know if there will be a 3.0. I was thinking, what would it be? We'll see.
Yeah, that's right.
Yeah, and thank you all for attending. Hopefully, we'll see you on our next CPD next month. Good night, everyone. See you soon.
Yeah. Good night.